Hello everyone, Trey here, and in today's lesson, we're going to work through a problem called first bad revision. And this is an interesting problem because it's one that seems maybe a little broader than it is, but really what it boils down to is a modified version of binary search. And we're going to code that from scratch, and then this is really a learning outcome you can take with you through any binary searching problem, understanding how to do it, and also modify it as needed. So the problem says, you are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions and you want to find out the first bad one, which causes all the following ones to be bad. And one thing to notice here is that the versions start at 1 instead of 0, which will come up later in the problem. And you're given an API isBadVersion where you pass a version number and it will return a boolean true or false if the version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. And when it says minimize number of calls to the API, it's really just saying get the best time complexity you can or the fewest number of operations. And let's take an example. Here we say n equals 5 or the total number of versions, and the bad version is 4. So if we call isBadVersion on number 3, it will return false. If we call isBadVersion on 5, it will return true. If we call isBadVersion on 4, it will also return true. And 4 is the first bad version, and that's what you return as the solution. So you see that before 4, they're all going to be false, and after 4, 4 and beyond, they're all true. And let's visualize this a little bit. And instead of using the variable n, I'm just going to say total versions, which is 5, and the bad version is number 4. And good versions will be labeled with a G, and bad versions with a B. So we have G, G, G as 1, 2, 3, and then 4 and 5 are B, just like we just saw. And if we wanted to solve this brute force, we could just start at the beginning, number 1, and work our way through until we found the first bad version, which is the first one that returns true. So if we say isBadVersion of 1, it returns false. IsBadVersion 2, false. IsBadVersion 3, false. And then isBadVersion 4, it returns true. So you return 4 as your answer. And this is just a linear O of n time brute force scan. So let's actually implement that just to see how it's done. So we'll say let current version, and remember we started at 1, and current version will go until less than or equal to the total versions because we actually want to check the last version in this case. And then we go to current version plus plus. And then all we do is we say if isBadVersion of the current version. If this returns true, we return current version. And like we said, the first one we know since it's done linearly and all the ones after that first one are bad, the first one is the first bad one. And I just wrote this helper function here, isBadVersion, where it takes in a version number, checks it against this constant, and we're using the same 5 total versions and 4 as the first bad one in that example. And then when we run this, first bad version of the total versions should return the same as first bad version, and we see it does, so it returns true. Okay, so now we understand the linear solution. Let's dig in and figure out how we can optimize that. So now instead of that small example, let's visualize much more data. Let's imagine there's 1 million data points and only the last 3 are bad. So if there's 1 million, you would have to go through all but these last 3 until you found that first bad one if you're doing this linearly, if you're scanning. So there's a lot of repeated work here. We're doing the same, checking if it's good so many times before we get to that bad. And we wonder, why can't we skip some of these? Why can't we move past a few and then get rid of chunks of them at a time? And also we can see that there's this unique ordering here. It's not necessarily the same ordering as if integers are ordered in ascending order, but we have these buckets. We have all the good ones, then all the bad ones. So we can kind of take this knowledge and think, how can we hone in? Instead of scanning them all, how can we make jumps each time? Because if we hit, let's say, 1 point and we see it's good, we know all the ones before it are good. And then all the ones after it might or might not be good. If we hit a bad, we know all the ones after it are bad, and that first bad one must be before it. So it is ordered, and there's a lot of repeated operations here, and we can use this ordering to make big jumps. And this is where the binary search comes in. So now let's look at a problem where we have 5 good ones, 4 bad ones. So total of 9 versions where the first bad is 6. And the way we do a binary search is first we set our lower bound, this left side, and we set the upper bound, the right side, and then we go to a midpoint. We're going to say, okay, is this midpoint a bad version? It's not. We can see it's not, so we want to move our left up to this midpoint, and we're also going to go +1 because we know this isn't the bad one. And we say, okay, let's repeat this again. We have our left lower bound, and we have this right upper bound. And we see, okay, this time our midpoint is bad. And we see also that there's 2 points in between. There's not an exact midpoint, so we're just rounding down for the midpoint. And we say, okay, this midpoint is bad. So we know that the first bad one must be before it. So we're going to bring the right one down to this, or not before it. It could also be this point. So we bring the right to this point because it can either be this point or one before it. And we say, okay, let's do it again. And our left and mid have converged because there's no more midpoint since we round down. The left point and the midpoint are the same. And now we go to the right point. We say, okay, is the left bad? Or sorry, is the midpoint bad? The same point. And it is. So we say, okay, we bring the right one in again. And now the points are the same. The left is no longer lower than the right. They've converged. And we say, okay, well, we know that our left one must have been on the bad. They converge to the same point. So this must be the first bad one. First bad version is number 6. So let's talk through this logic a little bit to see what we did. We performed a modified binary search. Instead of looking for a specific answer and returning it, we kept bringing these bounds in until they converged on the exact point that we wanted, which is where it transfers from good revisions to bad revisions. And we used a while loop because although in this case we would maybe know the number of operations, it's much easier to just move these bounds in until you get to the point you want. And if a revision is bad, we set that point as the upper bound. So if the midpoint is bad, we say, okay, this could be the first bad one, or it might be before this. So bring that upper bound exactly to this point. And if a revision is good, we say, okay, the first bad one must be to the right. It's definitely to the right. So we move it to that point +1, where it could land on the bad point. And then whichever one gets to that first bad one first, the other side will then eventually converge to it. So if it's if the left side hits a good one that moves up 1 to the first bad one, then the right one's going to continue to come in until it hits that point. Or if the right one, if the midpoint hits the first bad one, and then we move the right to it, then the left one's just going to come converge to it. Either way, they eventually converge, and you know that that point is going to be the first bad one. And finally, you finish iterating, and once they do converge, you just return the left side, which will be the bad one. And now the final thing to discuss is how you find the midpoint. So we're going to say it's the lower bound plus half the distance between the upper and lower. So let's say, we'll work through an example. So we have, we start with version 1, we have 7 versions. So the distance between them is 6. 1 plus 6 is 7, obviously. And we say the midpoint is 1, the lower bound, plus half the distance between the two. And we always round down. In this case, it's just going to be 3. 1 plus 3 is 4, exactly what our numbers show. And finally, we only have 2 items, 1 and 2. 2 minus 1 is 1. So 1 plus 1 divided by 2 is 0.5. That rounds down to 0. 1 plus 0 is 1. And our midpoint is 1. And finally, let's just quickly discuss why log n is fast. How are we getting this improvement over the linear O of n time? And let's take that million again as an example. Well, if we scan through all of them, worst case, we're going to have to go through all 1 million items. But if you take log base 2 of 1 million, it's only 16.6. And here are some of the jumps you make. You start at 1 in a million, your midpoint is 500,000. So you would move to that. You've already eliminated 500,000 items, much, much faster. And then you're going to eliminate another 250,000. So let's say you're moving up to a million if it's that last one. Worst case, you're going to go 500,000, 250,000, 125,000. And it's going to be roughly 16, 17 times until you have absolutely converged. So it's much, much faster. All right, now let's implement this logic in code. So we have, let's set our lower bound, and it's going to be 1 because it doesn't start on 0, it's 1 based indexing. And then our upper bound is just going to be the total number of versions. And we said, while the lower bound is less than that upper bound, we continue to iterate. Then once they is no longer less, they're either equal, then we know we've reached the midpoint, or sorry, the first bad revision, and we return that value. So we need to calculate the midpoint. And like I said, it's lower bound. That's the distance between the upper bound and lower bound. And then you divide it by 2. That's the midpoint. And you say if is bad version of the midpoint. If it's a bad version, we move that right bound inward. So upper bound equals midpoint. And we put it exactly at that point, like I said, because it could be the first one. So we don't want to move past it. But all the ones after it are definitely bad. And the first bad one is possibly before it or exactly this one. If it's not a bad version, we know it's good. So definitely the first bad version has to be after this current one. So it's lower bound equals midpoint plus 1. All right, let's run that. That's our logic. We have this binary search where we're cutting it in half each time and moving our lower bounds and upper bounds inward. And there we go. Now we're ready to run it. And apologies if you saw a quick jump in the video. I had to debug a quick network issue and also fix a couple typos. But we hit run and we get our solution is valid. And now we've implemented our binary search implementation. And I think this is a great question because one, we saw how to go down from that O of n linear time solution, bringing it down to O of log n, and implemented binary search from scratch, and also modified it for the question's needs. So this is a great learning outcome that if you get these down, they'll be very helpful in your interviews. If you like this, hit like, hit subscribe. I'm having a ton of fun making them and I'd love to keep going as long as you find them useful. Thanks, and I'll see you in the next one.